Không hề.
Double
Double A plus. I have not done homework.
How are you
Electrodynamics.
following along?
Homework? What's homework?
in this class? Is everything making sense to you, or how's it? Like, are you following along well?
This
No, in
class,
here.
this quantum,
Yeah.
I have not understand anything. I have not. I'm not even care about it since we have qualified. I'm not qualified. I will.
You'll go back and read the whole textbook.
Yeah.
So we're all in the same position.
We're on the same page.
We will back in
We'll be back
all
after.
till
2 weeks.
after qualifier.
Yeah.
Yeah.
I'm just copying everything she puts down on the
Qualified has been instructing on everything.
Yeah.
Everything
With the
will be
E&M,
fine after
since you all
qualifier.
already passed the E&M.
No, we have E&M and theoretical.
Oh, so at least you've been able to study for that and do the review of the class.
Yeah.
That's good.
For classical work, we are doing it.
Oh god.
Y'all had a homework due for E&M.
Today, I have not done.
I did most of it.
Don't
but I
worry,
haven't
it's only 0.2%. 0.2.
Yeah. No, it's a 2%.
Yeah, it's a 2%.
Yeah, 2%.
Not
Like this
negligible.
He
semester.
was really, he was really generous this semester.
Yeah,
Not negligible.
but that 2% could not affect to only score.
Yeah, I mean, plus
You can
either
get
way,
A instead of A plus. Oh.
Oh, there is no A plus, so I'm not worried about that.
either way, you just do the homework next week. No difference.
Yeah.
No difference.
He doesn't care about. Hello.
Hey.
Hi.
Dr. Yu, do you
Yeah.
know who wrote the qualifier exam for E&M this semester?
I do not know. Actually, and usually Dr. David Brick, yeah, Chris David. Usually, he teach ENM. So.
For the theoretical mechanics.
Who?
Theoretical mechanics.
Theoretical mechanics,
Yeah.
maybe Dr. Liu,
Dr. Liu.
might be, yeah, I didn't do, so I just said thermal, I do, yeah, thermal quantum sometimes.
We have theoretical mechanics.
Theoretical mechanics, last time, a little bit challenging, right?
Yeah, we got the F star.
Yeah. Hopefully this time, not so difficult.
We are hoping so. We are expecting to easy questions.
Classical and quant. That's what I
You
have
feel
to
like-
pass.
I feel like that's how it's kind of gone on the ups and downs over the year. Whenever one semester no students pass, the next
Another all
semester
pass, right? So this time we all
Yeah,
pass.
in the classical exam, no one has passed in the fall. So this time I think
we all pass.
If I don't walk out of classical feeling like so good, then
Your
I have
expectations are high.
but then if I have months of anxiety.
You passed, right?
No, I still have to pass
Right.
classical and quantum.
You have two.
Yes.
Okay, so this is
And
the
this is my last
second
time.
Last time. You did pass, but at least, right?
That's
So-
where I was last semester, and I came to your office. I'm like, please help me.
And then she was like, he didn't ask about the Carnot cycle.
That's right.
You know, but I implied you several times. I said not only statistic but also thermal, please.
Thermal, yeah.
Right? Remember? I couldn't tell you that.
That's true.
Couldn't show you the videos, right?
And I'm like, oh, I know thermal. That's easy. This part
Yeah,
is
that's easy.
more. But It
We
all
had to
worked
work
out.
a lot of partition function.
Yeah, we did.
There was
Many
notations.
hours. Many hours.
Yeah.
That's okay, you're a partition function expert now.
And I forgot it all.
It's like, oh, I passed.
Not enough room on the RAM.
Just write the results since we are going through the detail. So energy,
Are you like right hand ruling your pocket? Like,
He asked me how I was doing, and I just couldn't give him a thumbs up.
oh. You literally sat over there and looked like you're going in your pocket and you're like, right hand rule?
That's all I know. Current, velocity. Alright, I feel.
Jacob's going to sleep at night.
Yeah, I'm like. It's just like.
I will remember, if anything, the direction of current and current density.
I could not find out one attachment that 298 grading.
Oh, so.
What's the name? I don't.
Oh, okay, so you did it tonight.
298 and there is only one person left, but I could not find his attachment there.
so
Okay.
Could you
we,
check that?
well,
Yeah, yeah.
I think,
I'll see if I can do it.
Yeah. It's around,
yeah, and the F7, right? Yeah,
Seven.
yeah. Okay, that's fine. To solve this isotropic harmonic oscillator, we use first power series method. So for that case, we obtain energy. Do you remember? We obtain energy because the functions be finite, right? So then that the truncation gives us this condition. That is usually to deal with the potential infinite. I mean, from no boundary. So that is the most popular case. All right, so that is, and then the function. Remember, a function with first u, l, okay, r is equal to the if not index n and l. Since for given l, we have an equation, and then we have another constant here. And r l plus 1 power, that is when r go to 0, and when r go to infinity, we have this asymptotic behavior of exponential function. Remember this, right? Now, this one, since we need to make a truncation, so here this summation k, all are even number, right? Because r number all are coefficient 0 and 2k max. So a, k, r, k. Now, since this function depends on a given L and N, so here I'm going to add index text for that, but you will see that is dependent on N and L. So here I'm going to another index here. And we will see the ground state, the first axis, you see the difference. Okay, so the radial function now is also quantum number NL, R, which is U and L. We define U is R multiplied capital R, right? So that is this one. So that is F and L, R. Now R plus 1 divided by R, so this R to the L plus, R to the L plus 1 divided by R, right? An exponential, still keep this one. Okay. Then final, the wave function is a product of the radial part and the angle part, right? Phi, which is R and L is a function of radial R, and then this spherical harmonic. Here, just to remind you that AK is coefficient. We have the recursion formula to obtain the. Once we know A naught, right? So all the others coefficient can be obtained by this equation. all the information here. So now, okay, here, A naught is not 0, we need to determine. So here, I'm going to also, so you see here, this is L, but of course the E energy is function N, right? So that's the index with this. And here, okay. So N and L, whatever you have this R numbers be always 0. Now we're going to discuss what is ground state, how to determine the ground state, and first steady state, second steady state. I give you first 2, and then the later, the higher states you can do follow the same thing. So now let's first the ground state. We have energy here, right? So now we discuss the state. This is a function here, and you remember quantum number n from 0, 1, 2, or L also from 0, 1, 2, or the integer number n is plus minus L, plus minus L minus 1. All this, right? So that is all this. Now ground states n is equal to 0, right? Correspond to energy lowest part. So if n equal to 0, how about L? N equal to, oh sorry, this is not 1, this is L. A equal to K max plus L. So if A equal to 0, this we must take 0, and L is take 0, right? So there's no way, so only the 0, and of course then M is also 0, if L equal to 0. So the state is 0, 0, 0, which is R 0, 0. The linear function and the spherical harmonic also y 0, 0. Is this one. So now let's look this one from the table in chapter 5. We know this is a constant. R now, R 0, 0, R, which is here, right? F, N, L, N is 0, L is 0, R, and R to the L's power is 0's power, right? Here. And exponential. Okay, now we need to find F 0, 0. F 0, 0 is from this one. So how to obtain now? We are going to find this is summation k from 0 to all the even number and to k max, right? A k. Now I'm going to say 0, 0 because this is correspond to n and l are 0 and k. How much k max? If you can see here, k max can only take 0, or you can also look here, k max equal to m minus l, right? So here is m minus l, k from 0 to a 0, 0, k, r, k, which is m minus l is 0, 0 minus 0, 0. So that means this summation only 1/3, right? Only when k from 0 to 0, no anything. So that is a 0, 0, 0, r 0. That is just this first coefficient. So that became simple. Now let's see the finally. So now I'm just right here. So finally, you see here R is this is F 0, 0. So that is A 0, 0. And this is a 1, right? So that becomes exponential minus m omega 2 r squared. And we just keep this because we may do, we want to normalize or find this coefficient. We need to normalize it. So I didn't do this. You can substitute this number, but when we normalize, you know this spherical harmonic is the whole angle is 1, so we just keep this one. All right, now how to find normalization. So normalization is for this 0, 0, and well, that is the normalization and d omega, right? We're going to do this integral. Then we substitute this here. So the radial part here, radial part actually this is constant, this is only radial part, right? So I take a constant outside. And the radial part from 0 to the infinite, which is r squared exponential r squared d r, right? Yeah, this r squared here. And then the angle part, maybe at the moment I have a square. So here, actually, is in this one, right? We call this a square. So this 2 factor. And then this one is this one we know that this one is normalized, right? So now this. Now we are going to do this integral. This integral we can do integration by parts. Integration by parts. First, this coefficient, so I have a minus h bar Let me do that. And just give you other. I think we did it R squared, so. I gave that inside. Oh, okay, I didn't. Yeah, right, yeah, okay. So here, this term, this gradient that is 2r, we have a count minus m omega h bar, the 2r, right? So I have factor 2 here, minus of here. And then I need 1r here. So the remaining is r, not r squared, right? So here this is r. Then we do the r, then became only the exponential term. This one is 0, since when r go to 0, that's 0 multiplied this constant, and r go to infinite, this term go to 0. So now, that is this term, minus h bar over 2 and omega. And I have minus, okay. This integral, right? So I have a minus. So this integral is a half of pi over alpha. If alpha in this case is n over alpha, right? That integral we know. So it is. I have a minus here, so that is square root pi, and alpha is that. So that is pi h bar over n omega. That's equal to what? Okay, that's combined together. Minus minus become plus, so there's a factor 4 here. We have a factor 4 here, and then I all put into together. So I have pi h bar. This one come here is q, right? And m q omega q. Is to what? So from here we obtain the coefficient in R, which is this go to the right hand, so this is 2, factor 2, right? We take a square root. And then this one is omega, mq omega q and pi h bar q. Once we have these coefficients, so finally we have the ground state. If asked you to do that, you just follow this rule. So ground state is, this is 2, so here, right? In the calculation, 2, 4. And then the exponential, I just keep this y, I still keep here as a function here, even though we know in this case it's a constant. All right, so I got this ground state. So if asked you to try to find the other states, you actually, the key is try to find the I function. Once you this I function, you will have the total, since spherical harmonic function we already have it. Now let's do the second one. First, excited state. Okay, n equal to 1, right? According to energy. N from 0, 1, 2, 3. So the first excited state is n equal to 1. If n equal to 1, L equal to, if you remember, n equal to k max plus L, right? So if n equal to 1, k max either 0 or 2. So cannot take 2, right? That is you need your to judge how much k max you want. So in this case, since k max, I didn't. Whatever, just k max. Remember that is I think I read somewhere. It's always even number, right? 0 to 4, 0 to 4. So we cannot take 2 only to 0 when n equals 1. So it must be 1, right? Then n is 0 plus minus 1. Once you have this, so you know, okay, the ground, the first guess excited is 1 plus minus, there are 3 functions, right? It's just n, okay, just for n. So just n. So we have how many states? 3 states. So that's the 3 degeneracy for the first excited states. And remember, or I erase, right? Remember the degeneracy. N equal to 1. 2 to cancel 1 plus 2 is 3, right? So consistent with this. Okay. R11. Sorry. And Y1N. I erase the R. R11 is F11 R L equal to 1, right? And exponential minus M omega R, right? So, yes, okay. So now let's do this. I keep this one there. So now F11 is by definition we k from 0 to OR even numbers to k max. Now this index or coefficient AK is 1, 1. Yeah, yeah.
Wouldn't the first excited state be, say, n equals 0, L equals 1, or L equals 0, n
Good
equals
question. Remember the energy. Energy only depends on the quantum number n. So that is gave us energy with the first ground state energy or first excited. But n given, so we are going to discuss possible L and K. That makes sense? Okay. So here, now, as we know that the K max is equal to M minus L, right? And now, now N is 1, L max, so that is still from 0 to 0. is from 0 to 0 minus, one minus 1, sorry, 1 minus 1, right? A1, A, and the 1 minus 1 is 0, so only still a 1 constant. So, but this one is 1, 1. So even though it's all are A now, but they are not same. Okay. Then we have this exactly 1, 1, n, sigma I, which is here, right? So that is A1, 1 now. Since F1, 1 is only a constant and R to the first of it is R, and Y1, n, I, and exponential. For this one, chapter 5, we have table, right? So you can also obtain that. But I still want to keep here since we are going to normalize to find the coefficient. We just apply this normalization behavior of this spherical harmonic. So now, how to obtain this one? Again, we are going to take the normalization. So integral the square of this function whole space. That's equal to 1, right? Then that is equal to radial part. Radial part A, 1, 1 now is a constant right here outside. A, 1, 1 now. Square. Then the radial part from 0 to the infinite. Again, but now here we have R. So we have R and square. So we have R square here. Exponential minus n omega 2h, to h. Since we have also square, right? So this is h bar, R square dr. So we have R to the fourth power. Here, because it's square, right? So then here this factor 2 disappear, right? And then the remaining is the spherical harmonic, which we know that is normalized. And we do not substitute details. Is equal to 1. So that is constant. And again, we are going to do this integration by part. So this is R to the fourth power. Then they, again, we have something like this, where we have this factor like this, minus 2 n omega. And inside, we need this R to the fourth power, we need 1 go to here, so we have R cubed, right? So that's R cubed. Infinite and minus. Now R cubed, we do this so that we have factor 3. R squared exponential minus 100. The first term 0, right? This one still 0 because when R goes to 0, 0, R goes to infinite is 0. Then the remaining this part. This part, if you know, is like this. The same thing, but we have a minus 3 here, right? So I just jump to the final. This one, and we have another factor here, right? We have another factor here. So actually, this is square. And we have a minus 3. We have also minus half, this one, right? Minus half, and this alpha. Okay, so this is a plus, this is a plus, so we have a 3 over 2. And this is factor 4 here. Then we have 3, and then you can also observe that into inside. Then finally we have yes, okay, 3 square over 8. Okay. Because the square is 4 multiplied to the 8. And then this one. So that is I HRQ MQ over MQ I equal to 1. So we find this coefficient for the first second state, even though it's A0, but it's correspond to the N and L equal to 1, 1. So finally, this coefficient is, just take square root, so that is 8 over 3 MQ on Q or pi H Q. And finally, we will have the first exact state, which is the generic depend on M, but M is only follow the spherical harmonic YL, 1 YM, right? So that is then this one, 8, 3. These are similar like in this ground state, right? And R right here, R here on this one. Y 1 and second part and exponential. Okay, so think about how to just leave the question you do yourself, how to obtain this one when that corresponds N equal 2, right? So N equal 2, think about K max can be 0 or 2. If K max is 0, else be 2 or 0, right? Okay, that makes sense? K max is K max is N minus L, is 2 minus L. So L, if L equal to 0, K max is 2. So you have N 0 in this case, F2 0 and F2 2. Two these functions. And then you get hyperdiagonal. So you have, this is a 2. Okay, if L equal to 0 and M 0, and 2, 2, M. Right? How many? This one's 1. This one's 5. The diagonal is 6. The diagonal is 6. But you have 2 sides. And then you will see you have a coefficient, not only 1. So just leave this for you to play. Okay, this if we use the power series method now, I'm going to also go through another method, which you already familiar with, that when you learn the mathematical physics. So that is complement hypergeometry method. Maybe you'll get the same, right? So that's the different method. So how to use this one? I use this even though the textbook didn't deal with that, but I think you're already familiar with this, and you will see actually all the problems can go to the general complex hypergeometric method, depending on how this AB, I mean this the function is a constant. So let's give you this one, and when we deal with the hydrogen atom, you will see also follow this equation. So you will see how to play with this general method. Okay. So in order to do this, let's first define. I'm going to rename the variable, so define the low, which is alpha r. So alpha is square root m omega h bar. If I define this, so now let's go back to see, we have this differential equation, radial differential equation in term of u is, remember this. So this is plus 2m e over h bar square minus L plus 1 r square minus m square over h bar square r square u r equal to 0. That is equation, right? Now, so I'm going to, so I'm going to multiply alpha square both top and bottom, so alpha square, alpha gamma square, which is the low square, right? Plus, so here I have alpha square to m e, alpha square h bar. Then this one minus alpha square L plus 1, alpha square r square plus this term already. Can I erase this part? Okay. This one is already alpha and minus 1. Minus alpha to the fourth power, right? This one. Alpha square is m omega over h bar, so this square is. So you see here, I'm going to cancel the alpha square here. This go to alpha square. Then you can see here, this is reduced to partial square. U now replace alpha r by rho, partial rho square. For the second term, I'm going to use a constant c. C is this 2me over alpha square h bar square minus. So here this is L plus 1 rho square minus minus rho square. U is from the rho equal to 0. So C here is 2me over alpha square h bar square, which is equal to 2me alpha square is m omega over h bar square. So m cancelled with alpha omega h bar. That is constant. Okay, so that is the equation here for rho. We are going to use the marvelous rho. Now we look first again the asymptotic here. First, we know go to 0, and as we analyzed previously, right? We know that this is go to 0, so this is a constant, and this term dominates. We will have minus L plus 1. Okay. So the solution, okay, but who knows the solution is like which type? If you're familiar, if not, I give you this one. The same thing we analyze is L plus power. If you what you can do is to check. You substitute this into this formula, you will see this equal to 0. Right. Okay. You will see this is yes, that is a solution for rho go to 0, and yes, that is convert, it's finite, right? Then for rho go to infinite, we will see this term will small, so this term dominate. Then we have a partial square u, partial rho square, minus rho square u equal to 0. this solution we have to make, right? Because this is a negative, so the exponential should be real. Solution, when I say solution is physical acceptable, there's another one is low minus L that we drop because that's diverge. This one also, because we already analyzed this, so that is exponential go to the minus. We take the negative part, not the not this positive part, since we drop that one, which we divert. So that is a physical, right? Just say, okay, acceptable solution, right? That's correct. All right, so when we know this, then the U as a function rho has behavior which include this asymptotic behavior, then the general function I'm going to say F rho. And we know, so the L plus 1 power is exponential minus rho square over 2. This way, similar as the power series, before you use power series, you also need first analyze the asymptotic behavior. Then we are going to apply either for F function, right? For this one, either we use this power series method or complement hypergeometric function. So now we are going to try to find the equation for the F log, right? How to do that? If we have this formula, we are going to find, this is a node derivative, right? And find this one. So now let's do this one first. First order, partial U partial rho, which is here. You do the first partial F rho, partial rho, and rho A plus 1 exponential. Then you do the second, okay. Second to this one, so that is L plus 1, now to L's power, and F rho exponential 2. And third one is this, right? That is minus 2 to cancel, right? Minus rho. So minus rho L plus 2, right? Here we have L plus 1, we have another rho. F rho exponential. And this is okay. There's 3 terms. Yes. So I just make exponential, take outside, so inside is, since we are going to do the second order derivative, right? Rho L plus 1 plus L plus 1 rho L, right? Rho minus rho L plus 2. Then we look the second order derivative of U with respect to rho. This one a lot of details, right? So let me okay, let me get the first step and final step. The first step, I do the derivative inside this parenthesis. There's a square parenthesis, so that is second order derivative of F rho partial rho square, and keep this one. Then I do this plus L plus 1 rho L and partial F rho partial rho, right? So I have 2 terms here. In this term, plus L multiply L plus 1 and rho L minus 1 F rho, and then plus L plus 1 rho to L and partial F. And this term minus L plus 2 rho L plus 1 and rho minus rho L plus 2 partial F rho partial rho exponential. That is first, and then second one is inside this parenthesis here. I keep here. Partial F rho, partial rho plus L plus 1 plus L, right, L minus L plus 2. Outside is minus 1. So we have several terms. Then we combine the in terms of second order derivative, first order derivative, and zeroth order. So now I'm going to give you the final. Or we have exponential, right? So take exponential outside. We have a first, second order derivative. Multiply this term, this still keep here, L to L plus 1 power. Then the first order, all the first order partial derivative together. And the inside is 2L plus 1 L to the L's power minus 2 L to the L plus 2 power. And the zeroth order is L plus 1 L minus 1 minus 2L plus 3 L plus 1 plus L plus 3. And finally exponential. This is second order. Second order, yeah, here. Now, that is this part, right? So now we are going to look at this part, right? And then we are going to add together, right? So then the C plus C minus L plus 1. Here, I substitute this U is here, right? So I have multiply this inside. I have a 0 L plus 1, right? This one. And take F, this one outside. So then minus L plus 1. Then here, this is L squared minus, right? Then I have a L plus 1, so that is L minus 1. L minus 1, right? And the third term is a square, so that is L plus 3 minus L plus 3. Yes. Multiplied F rho and exponential. That is equal to C minus L plus 1. Right. So now, this is this term plus this term. Now let's see. There's some term we can cancel. Here. Right? L to L plus 3 term. This is a plus, this is a minus, right? F multiply this one, right? So that's cancelled. Another one is this one. This one, L minus 1, you can see here. This plus, right? This minus. So this also cancelled. Then the remaining part is this one. This first order is still here. And this zeroth order, we have this one and this one, right? So now let me summarize. The function of differential equation for the F law finally reduced to obtain this here. Since I use which one I use. Okay. I use this. The partial second of the partial, clarify the partial square. You will see here, I'm going to take this low L plus 1 outside, and also this one outside, since this has all the terms. And then the remaining term, because that is the remaining term, multiply this one with exponential, so that can cancel. Then finally, this is plus 2 L plus 1, L minus L, first order. And then the remaining is this, or the C, okay, minus 2L plus 3 F equal to 0. I take this because we have this factor exponential power part all take outside, so then OR cancel. Then now this is the equation for F. But so far we still cannot see which type of the differential equation can fit this one, such that we can directly get this solution. So we need again to manipulate this one by define x is a row square. So dx is 2 row, 0, right? And then the row is here, row is square root of x. So here that is 2 square root of x. Let me keep that back. Okay, just here. 2 square root of x, 0. So dx 0 is 2 square root of x. So now here, replace this one. Then you will see here now, again, we need the sum of, we have first order, second order, also, but the first partial derivative is partial f rho, partial x, partial rho. Then here I have this one, so this became function x and 2 square root of x, right? And this one. Then the second order derivative of partial f rho, partial rho square is partial. I already have this one, right? Partial f, partial rho, partial x, and this one I already here. So that is this one. And this one again is a square root of x. So finally, we do this, we have a second order derivative and keep this one, and then another one is keep this first order, then we have a factor half cancel, right? Then they go to, so now I give you final, so we have a 4x 4x square fx over d. It now since only function x, so we either use partial or total. X square plus 2 partial f x partial x. We're almost to the end. So now we are going to substitute these two together. Then it's this part just replace f as function of it and f as function x, right? So only this term, and this one also replaced by x. So finally, we substitute this one here, this one here. Finally, we will have the equation, differential equation will reduce to in terms of x is here. Let me give first this step and final. I think that is very clear. Okay, x. M code I use the code plus L plus 3 half minus x dx minus quarter 2L plus 3 minus c. Minus c. Fx equal to 0. Now, familiar with the complex hypergeometric function. General complex solution is we have x, second order derivative, dx plus b minus x, and plus minus a. So now we compare both. Here we have x here, second, and then here b, some constant minus x, right? So now we have b. Then this all are constant. So here, compare with this one, we have a b is equal to L plus 3/2, right? And a equal to 2L plus 3 minus c. So if we define a and b like this, that is nothing like this. And then you can immediately got the solution, right? Solution, mathematically, then we are going to discuss whether it is physically acceptable or not. We have this as important here. So solutions be confluent hypergeometric function, trigonometric function. There are different types, like kind 1, 2, but let me just use this general case. I hope you will have. So solution f(x) be function. Now this is a general common hypergeometric function, which is f function a give a constant, the coefficient a or constant ab and function x. It is a series, right? Remember? Not sure. So that's b. Okay, s from 0 to infinite. And we have the numerator, we have a as a function s, and x, s power, denominator b, given s, and s power. That is, right? It is, okay, we know that. So here, AB here, right? So A, if you, I just try to help you remind, if you remind this group, multiply a plus 1 until a plus s minus 1. That is for giving s. This actually is a product, right, of this similar for b. It's 1 multiply b and b plus 1 and until b plus s minus 1. So immediately we got the solution. Now the only thing, difficulty or challenge is how to manipulate this different equations such that we can derive or convert to the confluent hypergeometric method equation. Then we can find that this coefficient. We immediately got this solution. Okay, now finally, u as function rho. Right? Rho is defined as square root of x. So finally, as in terms of rho here is rho is asymptotic behavior, and then this function of confluent hypergeometric function. Now f a b x. Now I'm replace x in terms of rho. X is rho square, right? That is. But now when we have this, we are going to discuss again. It is finite or infinite when rho go to infinite. Since when rho go to 0, this controlled by this controlled. But here, how about this one? Is it finite or not? So we need, since when rho go to infinite, this function go to where? You see here, x is rho square, right? So that is rho 2x as a function factorial s. So that is exponential, right? Yes.
Are all of these parentheses being multiplied?
Yeah, just multiply in here, right?
Yes.
Yeah. Right, let's follow like this because you know, if you know this, I think you're familiar with the exponential that the Taylor expansion is like this, right? This one is 2 and this one is factorial. So you can see here u rho when rho go to infinite is controlled by, this one is fine, but the definitely is this one. Diverse. So even though we already discussed the U function, we have this like asymptotic here, we want to have this F. This must be finite, right? So we need to truncate F to finance here over polynomial instead of infinite. Here infinite, right? So if finite, it is finite. So how to do that? That means if we want to make truncation, is this F. Let's go back to here. F. You use rho or ux is fine. That's fine. Which is that's here. Is here. S from 0 to the S maximum cannot go further. That is the way we're going to make a truncation. And same thing, this is the second time we make this type of discussion, right? So then this coefficient here, A, S, B, S, and rho 2S, S factorial. If this case, what this means, if we truncate, means the coefficient A, S, that is the S max, equal to A plus S max. Well, okay, this is a minus 1, right? So the A, S max plus 1 is equal to 0. It's the higher term, right? So with S from 0 to S max, okay, those are finite, but we want to have all the above the S max to be all 0. Then how to control that is numerator, the coefficient we can control. So that coefficient means correspond to the A, x1 plus 1, right? So now, that is equal to A plus S max plus 1 minus 1 is equal to A plus S max must be equal to 0. That is condition, right? That is how to analyze. Okay, then we can find, from this condition, we can determine the unload energy. As we use a similar idea for this, use the power series method. So, okay, what is what is the A? So A equal to, okay, that one, A equal to S max, right? So A, where is A? A is here, right? So that is quarter 2L plus 3 minus C. And that is 2L plus 3. Remember C? C is 2E over H bar omega. So then I can remove, or you move this term to the left-hand side and this term to the right-hand side. So we're going to find energy is very easily. Energy is H bar omega 2S max function S max plus L plus 3 over 2. Now, I'm going to define or introduce a quantum number. Let's see. So n equal to 2s max plus L. Remember with this? We use n, right? This one actually is k max, which takes even number. And remember we define k max equal to n, capital N. So n can from 0, 1 to all the integer number, right? Just remind in the power series method. So now S here, S can start from 0 to all the numbers. So you will see here, S max from 0, 1, 2, all the numbers, and L from 0, 1, 2, all the numbers. You got the same energy, right? Of course, the function here is like this component have a geometric function. You can see if you want to make a conversion compared to the power series that F and L. It is possible, but we can still keep this one here. So now, finally, energy will be here, so you can discuss as what you want about the energy of the function, right? Same thing. Then this function of the radio function as N L. The N L, because here we know for the F, for given L, we have one function. So that depends on L. Now we introduce another one. So that is again function of N and the index. Thus be R, U, and L, R. And U, remember, is we use rho. Rho is alpha R, right? So that is some constant here. I can use in this R L first, right? Here, right? Rho is, remember, rho is alpha R, right? So we have some constant alpha is the square root of m omega alpha. So that's a constant, but here that that is just evident. Right? R is U, right? So then that is 2 power, and we have this term, and this one is this. So there's some constant here, because we observe constant to all the others I keep here, that is minus, that is a square, right? So that is alpha square R squared. So that is m omega, and factor 2 here, 2h bar R squared, right? That's the same thing with the power series, we have this one. Then the remaining F and L now is AB, right? So now A is, okay, let me write down A and then B, L plus 3 over 2. And the variable low square is alpha square R squared, so that is m omega H bar R squared. This one can also write in terms of this Lagrangian polynomial. Now we use this coefficient here. I'm going to, why A is here in the HR squared. Okay, and A plus half, M minus L half. Okay, N L M, which is radial part plus this here. If you remember, A is this one, right? A is this one. So when you substitute the energy here, this is energy into here, and manipulate the wave form, that is this one. Omega cancel, so became is n half 3, right? It's cancelled, so twice, and then use this term. So very easily you can obtain. This is A. This is a B. This number. When you substitute E. Familiar this one. Okay. So now you can see energy, whatever the method, we can obtain the same formula here. If they function in terms of this or of this power, but this is equivalent. So if you really want to find the equivalent, you need this see this comparison, but I just leave here for just the majority is try to how to apply this method, right? All right, so now for this part we discuss finish. Now we go to the hygiene item. This is the last system in this spherical harmonic coordinate, spherical coordinates we are going to deal with, and this one you're familiar with that. But I'm going to only use the confident hypergeometry method. The textbook still use the power series, so you can easily see, read that one and do yourself. But for the confident hypergeometry method, I want to do again since they are slightly different. How to derive that equation. First, let's consider hygiene item. We have this the proton at center, right? An electron at the move around as a orbit. Okay, this is R, right? The distance, relative distance between this. Now, since this is a two-body system, if this is relative, the absolute coordinates here, so we have R proton, R electron, right? Then there are so to deal with this two particle or two body system, we need first try to see if we can make this separable. And the other idea from this theoretical mechanics chapter 3, we already learned this center force form, right? So just remind you now the function, because this is a function is of total the hygiene item, right? The function of the position of electron, the position of proton, and part, right? And if this gives us this so that is function. Then the Schrödinger equation, so that is one. So Schrödinger equation, time-dependent Schrödinger equation is I h bar partial. I'm going to use capital, so I'm not going to use a lower for the relative case. So now this is R E R P T partial T equal to the total Hamiltonian. The total Hamiltonian is we have kinetic energy for the electron or proton. So now to then we do this E squared minus H bar squared MP squared. That is two terms. Kinetic energy operator of electron, kinetic energy operator of proton. Then the interaction of potential energy between the two, which is a Coulomb potential. Let me first use VR. That is for the two-body system, right? To solve this time-interdimensional equation. And then the next step is we try to see if it is separable. So let's do this one first. This is Hamiltonian, right? Hamiltonian does not depend on time explicitly, right? And we discuss in the either the chapter 3 or the last postulation or the chapter 4 when begin discuss. When the Hamiltonian does not depend on time explicitly, so the time-interdimensional equation decoupled into two. One is only time-dependent function, which is exponential. Another is time-interdimensional equation. So this equation, so this Schrödinger equation is decoupled into two, right? Just to remind you here, we have the form. We have the function can be separated into the spatial function and the time-dependent function. I'm going to use phi, which is a function of only the radio E, R, E, and P, and it multiplied time dependent with exponential minus E, I, or H by P. That is first, the function set product can be written in the product of the radio, spatial part and time part. Then this differential equation became only the time independential equation, which is only this part, right? So 2 me grading a square minus h bar squared over 2 p squared. Here now I'm going to substitute this potential is Coulomb potential, which only depend on this relative position between these two particles. Equal to so now we have this time-dependent function formula is like a stationary state. Now, time-dependent Schrödinger equation reduced to time-independent Schrödinger equation. So we're going to solve this, and the unknown function is chi, which is only the function of the position. So once we separate, and then we can go further to separate this chi into the center of mass and the relative or reduced mass. Okay, that I just make very quickly. So remember, the total kinetic energy is a particle, you could say that this electron and proton, right? And we can also rewrite as a center of mass. I'm going to use capital R and relative. Because it's, remember that this is a very, you know, right? We discussed in the theoretical mechanics chapter 3 center force problem. So I just jumped to introduce center mass. So this is a kinetic here of a kinetic energy of center mass, and that is relative kinetic energy. This is classical, you said. Okay, now I'm going to make a quantum just,
Dr. Yi,
yeah.
is this a constant squared, c squared?
E, sorry, this is a charm.
Gotcha.
So you can also, since we know from quantum, classical to quantum, just make this quantity to the operator, right? So what is this? This one, okay, now I'm going to write down. This one is 2 now. The total mass, right? Center mass is total mass, and then grading respect to the center of mass. That is it, and then the relative to we use reduced mass mu, right? Okay, if that case, then we come to here, we rewrite this one. So you will see here, it is now, let's come to, okay, so now I have the minus h bar squared, we take the time independent equation. So, time independent equation, which we are going to separate in terms of center mass and relative. So then you will see this differential equation will become simple or easier to deal with as a single particle system, not the two particle. Okay, so then here minus here this one, right? This two term is replaced by this two. So NP minus H plus E. Minus, now here, I already replaced this one by relative, right? So by this one, and capital R is MERE plus MPRP ME plus MPF, just like this. So here this R is not one, and here this is R. Okay. The chi here, since I separate here, you will see this only function the relative position over the center mass. So the function here, that one I'm going to introduce as only function of the center mass multiply the function of here. Since we replace this by this relative center mass and relative coordinates, so that can be writing in the product. So here I replace this chi here by this center mass and relative, and since they are separable, if you can see here, they are separable, and then we can also make this a product. Then this equation again further reduce. So here still two variables, right? But if you divided this both sides, then you can see here you have just write the result and I'm going to explain. Minus right, so I divided this product both sides. And then I do this one here, you see this is only function of capital R, right? Does not affect this Laplacian operator, only up to this one. So I can move this in front of this, right? And then they cancel because it's denominator. That makes sense? Okay. Similar for this one. For this one, only apply this, so I keep here. But then there's this phi r in front of this, and the denominator has to cancel. And this one cancel this one. So now we have this. And we have this. You have another class. Okay, let's keep here. And you almost know that we have a two-type equation. If we do not have a class, we can extend a little bit time. So let me start here. Like your qualified exam, this time you passed. Oh.
Yes,
Yes.
definitely.
Yeah.
So, just for, I guess, clarity and maybe peace of mind for me. So, not everybody in this class saw some of these things in math methods. So, how worried should we be if we've never seen confluent hypergeometric functions?
You what I require you is I have this this step by step, right?
Yeah.
You just follow something like that, step by step. And if in the homework or exam, I may give a system, but you just follow same idea. How to, for example, you define the law, and you made it and define x. Try to get into that equation. Once you have to, just use that solution. That's all. You don't need to go to the details. Just how to manipulate your different equation to that. To match that equation, that's all. And then you use the solution. And I do not ask you to go to details even as each individual, but just idea.
Okay.
Yeah.
Bye bye.
No, not about the homework. This is about the
This one.
lecture. So,
Jump.
going back to
Yes.
the original question I asked you, so
Yeah.
with the first excited state,
Yes.